Okay, so thank you everybody for still being here, and also the organizers for letting me present you this talk. My name is Alba Vidal Garcia, and in behalf of this collaboration, I'm going to talk about the probes of a large turbulent reservoir in a galaxy group at high redshift. And as my talk is on the probes of turbulent dissipation, I start by showing this beautiful picture of photoluminescent plankton on the breaking waves of a tropical sea. And this is because plankton shines when trapped on a strong velocity shear, and as such is a tracer of energy dissipation in turbulence. And to do a comparison, CH plus will be like the plankton of the circumgalactic medium. Galaxies grow in simulations like this one that I show you here by accreting cold streams. And the momentum exchange between these cold streams and the rotating galaxy in the dark matter potential well can be so violent that a large turbulent interacting region can be created around the galaxy. So while feedback from star-forming regions and AGNs is routinely observed through powerful outflows, the observation of this accreting gas remains elusive. A way of observing this accreting gas is by detecting redshifted absorption lines with respect to the galaxy's systemic velocity. And this has been done nearby in 2 local starbursts through the profile of CH+. One of these local starbursts is MEG2, of which you see a beautiful picture here that also has an outflow and a fountain that has been traced and observed for traces of gases at different phases, some of which you see the profile in the central panel, such as CO, H1, C+, or CH+ here in red. These profiles of CH+ is an inverse PCMI, where you see a redshifted absorption, which is tracing the gas that is inflowing back to the galaxy in the fountain. This black bar here is the velocity range of shocks seen in SIO. And as you see, it corresponds with the emission of CH+ of this profile. Here I do a zoom on the Milky Way absorption, in which we can see how similar the velocity ranges of CH+ absorption and H1 are. Another local starburst where CH+ 10 has been traced is NGC 4945. You see here the false color, where you can appreciate the disk and the H2 emitting nebula. And in the central panel, you see the CH+, H1, and HF spectra, and you see how in the 3 of them, you see a prominent absorption. The inflow rate of the gas has been traced through HF and is of the order of the star formation rate of the galaxy. Finally, I want also to notice that in the Milky Way, the 2 profiles, again, of H1 and CH+, are very similar. This is telling us that probably these 2 lines arise in very similar environments. So why CH+? This is because it is a very precious tracer due to its unique properties. It has a highly endothermic formation, so we need suprathermal energy to form these molecules, such as turbulent energy. It is highly reactive, so it has a very short lifetime. So this means that we can only observe it where it forms. And unlike most molecules, it is enhanced by UV photons instead of photodissociated. And unlike all light hydrides, it has a high dipole moment, so its J10 transition is difficult to excite through collisions. So the absorption lines of this transition trace diffuse gas, and the emission lines trace high-density gas seen in shocks and photodissociation regions. So due to all these unique properties, CH+ is a tracer of turbulent dissipation, even if this morning we saw that this was crossed out. And the contribution of dissipation to the formation of CH+ is still under debate, so not completely trusted. So anyway, we can use the absorption lines of CH+ as a counter of the molecules formed in the absorption beam. And if we assume that they are caused by dissipation of turbulence, we have access also to the turbulent energy transfer rate. So now let's move to high redshift universe, and I present you here the CH+ 10 spectra in a subset of galaxies that we have observed with ALMA. These galaxies, as you can appreciate in some of the continuum images of the objects, are extremely dense and at a redshift of about 2 at cosmic mean. As you see in the spectra, often the emission and absorption coexist. And I wanted also to show or to raise the point that in 16 out of the 18 starburst galaxies that we have observed, this line appears in absorption, which is telling us about the coevolution of the diffuse phase and the starburst phase. One of the targets that we have studied is, or we have observed, is this group that I present you here that consists of a starburst galaxy and an AGN, and these two nebula that are not seen in submillimetric domain. Some of the properties of the group are quoted here, such as the star formation rate of the starburst, that is almost of 1,000 solar masses per year. It is lensed by the cluster Abel 370, and the time of the starburst phase is of the order, well, it's 66 million years, taking into account the molecular gas phase. Here I show the continuum map and the CH+10 line maps integrated over these two velocity ranges. And in the bottom line, you see the spectra towards the starburst and the AGN. These two boxes, the blue and green one, represent the velocity coverage of the absorptions of CH+10 towards the galaxies. And as you see, they are redshifted with respect to the galaxy's systemic velocity. And therefore, they are tracing in falling gas towards the galaxies at a velocity of about 400 kilometers per second. Assuming that this molecule is formed in situ and assuming also that they are caused by dissipation of turbulence, we can have access to the turbulent reservoir, the mass of the turbulent reservoir to be of the order of few tens to the 10 solar masses, and the radius of the turbulent reservoir to be of the order of 20 kiloparsecs. We can also see how large these lines are in emission and they are of the order of 1,400 kilometers per second in the galaxies, but not only, because we have also some emissions of CH+ in the surrounding part of the AGN that also show these broad emission line widths. Let me now present you the Lyman alpha emitting nebula you see here. And as you can observe, the brightest part of the nebula are concentrated around the galaxies, but there is a fainter extended part that goes up to distances of about 80 kiloparsecs. On the right, I show a position velocity cut taking along this cut of the nebula, where you can also appreciate that the broadest line widths are also concentrated around the galaxies, tracing outflows up to velocities of 1,000 kilometers per second. And in contrast, in the extended part of the nebula, we see how the lines are narrower and appear redshifted. So what do we learn from the comparison of CH+ and Lyman alpha observations? First of all, that the Lyman alpha emitting nebula and the extent of the CGM traced by absorptions of CH+ are commensurate, as we see in the plot on the left, where these magenta ellipses trace the extent of the turbulent reservoir calculated with two different duration of the starburst phase, and taking also magnification into account. In the central panel, you see the spectra of Lyman alpha in different directions of the nebula, and these green and blue boxes again represent the velocity coverage of the CH+10 absorption towards the galaxies. As you see in this velocity range, the Lyman alpha is self-absorbed. These boxes appear also in the position velocity cut here, and here I want you to note that the extended part of the Lyman alpha nebula agrees in velocity with this CH+ absorbing gas, which is telling us that these two phases are dynamically coupled, and therefore that this whole extended part of the nebula is also inflowing towards the galaxies as the CH+ absorbing gas. So what do we learn again from this comparison? First, that the CGM is multi-phasic, and very importantly, that all of it is inflowing towards the galaxies. We have also computed different position velocity cuts along the Lyman alpha nebula, and as you see, in this plot where I show the red and blue wings of Lyman alpha outflows. These white boxes represent the line width of the CH plus emissions that we have cut with these position velocity cuts at the position of each of the CH plus emitting structures and at each velocity. These CH plus emissions are do not correlate with the peak of the Lyman alpha emission, but they do coincide with the wings of the Lyman alpha emission. So this coincidence is telling us that at least there is some shock contribution to the Lyman alpha emission, because I remind you that the emission of CH plus traces UV irradiated shocks. Here I show you the CH plus 10 intensity map integrated over this velocity range, superposed to the Lyman alpha red outflow here. These ellipses trace some of the regions that are emitting in CH plus, and as you see, they lie at the edges of the Lyman alpha outflows. So this agreement in position and velocity is telling us that what we are tracing with these CH plus emitting structures are kiloparsec scale shocks that are located at the interface between the outflows and inflowing CGM. Let me say this again. So the spatial distribution of the CH plus emitting structures and the high velocity Lyman alpha emissions are tracing kiloparsec scale shocks with average line widths of about 1400 kilometers per second that are located at the interface between the AGN and starburst driven outflows of about 1000 kilometers per second and inflowing CGM at about 400 kilometers per second. The broad line widths that we detect for CH plus would imply a post-shock gas thermalized at about 50 million Kelvin, where no molecule would survive. So these broad line widths that we detect of CH plus are telling us about the velocity dispersion of low velocity molecular shocks, and especially those that are more efficient to form CH plus. The fact that we are tracing also CH plus emission up to distances of about 20 kiloparsec also mean that we detect shocks up to these distances. I wanted to finish by showing the prediction of UV irradiated shock models for the line intensities of CH plus 10 to compare them to several line intensities of the H2 molecule. On the left, you see the prediction for the intensity of CH plus 10 line as a function of pre-shock density and velocity. And this region of the parameter space represents the region where the line is most intense. And on the right, I show the intensity of different H2 lines with respect to that of CH plus 10 that has been already detected. And from these plots, we see that these lines that are two row vibrational and two pure rotational ones are at least 300 times brighter than that of CH plus 10. And these lines are measurable with MIRI onboard GWST for this object and for objects at similar redshifts. And if observed, they could give a measurement of the radiative losses of kinetic energy in the CGM shocks. And also the spatial resolution of MIRI could serve as a locator of the census of all the CGM shocks. So let me finish by wrapping up. So basically, I have talked about this galaxy group in which the redshifted CH plus 10 absorption lines trace the influx of diffuse molecular CGM at about 400 kilometers per second. The line width of this the line width of the absorption line and the connection between the fact that we observe it in situ and that it's formed by a dissipation of turbulence allow us to access the measurement of the radius and mass of the turbulent reservoir. The co-spatiality and dynamic coupling of CH plus and Lyman alpha lines allow us to infer that we are dealing with a multi-phasic CGM that is all of it inflowing towards the galaxies, and that there is at least some shock contribution to the Lyman alpha emission. The broad CH plus lines at the edge of the high velocity outflows from Lyman alpha is telling us that we are tracing kiloparsec scale shocks at the interface between outflows and the inflowing CGM. And finally, If measured, these H2 lines could tell us about the relative losses of the kinetic energy and the location in the CGM shocks. Thank you very much for your attention.